Hi guys, and welcome to another video. We are looking at grade 11 maths algebra nature of roots in this particular video lesson, and we've already covered the November 2019 paper 1 question on nature of roots, and we've done this in the previous video. We've also looked at the 2018 paper 1 that's in November, and we've looked at this particular question here, which is 1.3, and that was in the previous video. In this particular video lesson, we're going to be looking at what came out in November 2017, paper 1, nature of roots. Just to quickly summarize on nature of roots, remember that nature of roots, to describe the nature of roots, is to look at the discriminant, which is delta, which is b squared minus 4ac. And just to quickly review what I already said in the first video, if delta is equal to 0, our roots are equal. If delta is greater than or equals to 0, our roots are real. And if delta is less than 0, our roots are non-real. Also take into consideration that if delta is greater than or equal to 0, and if it's a perfect square, then our roots are rational. If it's not a perfect square, our roots are irrational. Okay, so make sure that you learn the summary for nature of roots. Then you'll be able to answer your questions a little bit easier. Alright, so they say, for which values of k will the roots be equal? Okay, and I just mentioned that to you now. If f of x equals to 0, has roots x equals to minus 5 plus minus the square root of 3 minus 12k squared over 4. Now remember that delta is underneath the square root sign, so underneath the square root sign is b squared minus 4ac, which comes from our quadratic formula. Quadratic formula is x equals to minus b plus minus the square root of b squared minus 4ac all over 2a. Now remember that the standard form of the quadratic equation is ax squared plus bx plus c equals to 0, a, b, and c. And if you complete the square of this quadratic equation, basically solving for x, you'll be able to come up with your quadratic formula. Now, let's get back to the question. It says here that if f of x equals to 0, has roots x equals to minus 5 plus minus the square root of 3 minus 12k squared all over 4, for which values of k will the roots be equal? So for equal roots, delta must equal to 0. So to answer this question, delta must equal to 0. Therefore, take what's underneath the square root sign, which is 3 minus 12k squared, and equate it equals to 0 and solve for k. So it will be 3 minus 12k squared, 3 minus 12k squared, 12k squared equals to 0 minus 12k squared equals to minus 3. I divide both sides by 3. What will I get here? Or rather by 12, the coefficient of k squared is minus 12, right? So minus 12, therefore k squared is equal to, minus over minus is plus, and here I'll get 1 over 4. Therefore, if I find the square root of both sides, it will be plus minus the square root of 1 over 4. Therefore, it's plus minus a half. So therefore, k must equal to either plus half or minus half for our roots to be equal. That's the solution to the first question. Now let's go look at the November 2016 paper 1. Let's see what came out here on nature of roots. In this particular question, we have 1.3. Show that the roots of 3x squared plus k plus 2 times x equals to 1 minus k are real and rational for all values of k. Now remember that the first thing we have to do is we have to write this in the standard form first, which is ax squared plus bx plus c equals to 0. Then we are able to work out what the discriminant is, which will be b squared minus 4ac. And remember that if we can prove that delta is going to be greater than or equals to 0 for all values of k, then the roots will be real and rational. Okay, so let's go and do that in that order. 3x squared plus k plus 2k plus 2 times x, and let's move this 1 and minus k over to the left hand side. So we're going to get plus k minus 1. And if we remove a plus sign, it will be plus into k minus 1. Remember, plus times k is plus k, and plus times minus 1 is still minus 1, and that will be equals to 0. So we've achieved our first step, which is writing in the standard form of a quadratic equation. Therefore, now we can work out delta, our discriminant. Delta equals to b squared minus 4ac. So now your b value will be that k plus 2. So it will be k plus 2 all squared minus 4. My a value is 3. And my c value is positive k minus 1. So it will be k minus 1. So let's now open out those brackets and let's see what we get. So here we'll get square the first term, k squared, double the product. K times plus 2 is plus 2k, times 2 is plus 4k, and square the last term there is plus 4. Minus 4 times 3 is minus 12. Minus 12 times k is minus 12k. Minus 4 times 3 is minus 12. Minus 12 times minus 1 is positive 12. So what am I going to get here? K squared, 4k, and I'm going to get minus 12k is minus 8k. Minus 8k, and 4 plus 12 is 16. Positive 16. Now I want to see whether I can factorize this. Let's see. K squared. Let's see if we can factorize this by inspection. K squared is k times k. Factors of 16 when multiplied together to give you positive 16, when added together to give you minus 8. That'll be minus 4 and minus 4. What do you notice about this? Well, this is a perfect square. K minus 4 all squared. K minus 4 all squared. So therefore, delta is a perfect square. And if delta is a perfect square, k minus 4 all squared, what does this mean? It means that our roots are going to be real and rational for all values of k. Because remember that for real roots, delta must be greater than or equal to 0. And for rational roots, as you can see here, remember that because it's a perfect square, it will always be rational. So therefore, we can conclude that it will always be real and rational. Once again, why is it real? It's real because delta will always be positive, which is greater than or equal to 0, and rational because it's a perfect square. So learners, that answers this particular question. If you haven't subscribed already, subscribe to JL Maths, like my Facebook page, Justin Lazarus Mathematics, and you can watch all videos in order of the work schedule on jlmaths.com. And I'll catch you in the next